Let H and K be subspaces of a vector space V. Show that the intersection of H and K is a subspace of V. So to get us started, we're letting V be a vector space. We're going to let H be a subspace of V. And we're also letting K be a subspace of V. So this is what's given to us. And to get us started here, let's think about a geometric interpretation. So we can pretty easily see this using Venn diagrams, but that's not sufficient here. We want to be able to show this algebraically as well. So here we go. I am going to let this be H, and we'll let this set be K, and then the intersection is the region I'm shading in between. So that's H and K. So if we actually really wanted to relate this to a Venn diagram, let's let this be the universal set V. We let our vector space be our universal set. So we can see that H and K are subspaces of that vector space V. So we can also visualize here that our intersection is to a subspace. But now we want to confirm this. So we need to show that those three properties are holding true. And let's give ourselves lots of room here. So we want to first show that the zero vector is in the intersection of H and K. So right off the bat, we can immediately start and say that since H and K are subspaces, then we automatically know by definition that the zero vector is in H and the zero vector is in K. So therefore, since the zero vector is in H and the zero vector is in K, this tells us that the zero vector exists in their intersection, which is what we wanted to show. So we have confirmed that the zero vector lives in our intersection, and we're ready for the second property. We now want to show that the intersection of H and K is closed under addition. And again, so actually let's let vector u and vector v be elements of the intersection of H and K. And in a similar method to step one, we can make a note that since H is a subspace already, then vector u plus vector v is in H by definition. We can also make a note here that since K is a subspace, that the sum of these two vectors, u plus v, is also in K. So therefore, since vector u plus vector v is an element of H and vector u plus vector v is an element of K, this tells us that by default vector u plus vector v is also an element of their intersection, and thus is closed under addition. So our second property is met, and we're ready to show our third and final property. So last but not least, we want to show that the intersection of H and K is closed under scalar multiplication. So let's let u be an element of the intersection of H and K, and and we'll let C be any scalar. Again, since H is a subspace, we know by definition that the scalar multiple C times vector U is an element of H. And since K is also a subspace, we know that this scalar multiple C times vector U is in K. Therefore, since the scalar multiple C times vector U is an element of H, and the scalar multiple C times vector U is an element of the subspace K, then the scalar multiple C times vector U is an element of their intersection. And so our third and final property is met. So therefore, the intersection H and K, or we should be more formal here, since all three conditions are met. So since all three properties are met, the intersection of H and K is a subspace of V. And that is our beautiful final answer.